For our embedded systems project, we chose to model a passenger lift that you would find in almost any building. The purpose of these lifts is to safely and efficiently move passengers and goods up and down floors. Lifts are one of the most ubiquitous embedded systems in our society, and very few people probably consider the logic behind them. Part of the drive behind selecting this project is I personally use a lift every day that has an annoying logic glitch. We also have extensive real-world experience with these systems, so explaining how they work is second nature. Our objective was to physically build a model lift that services 3 floors. Our lift includes a display for the current floor it's on, an arrival bell, and an automated door. We are controlling the system with an Arduino Due that utilizes a SAM3X processor. Because lifts are a mature technology and follow strict safety guidelines, our lift will not accurately model this design. The sole purpose of the model is to serve as a visual aid for our program logic, and this left complete design freedom. Our first design considerations were our fixed constraints, the main one being we couldn't choose a microcontroller. As a learning experience and cost-saving measure, we also utilized a motor and H-bridge from our power electronics course, which meant the drive had to be designed around a specific motor. We also wanted the project to be affordable. We identified our inputs as just user inputs from the buttons and the lift position inputs. Our system starts with the Arduino Due. Its main task is to control a DC motor. But to do that, we need to interface the motor so that we can supply 12 volts to it, control its speed, and control its direction. Here, we use a H-bridge. The Due supplies a complementary pulse width modulated signal, and the H-bridge supplies power from a power supply to the DC motor. Our user interfaces with the lift via a switch panel, but before the lift knows what to tell the motor, it needs a position input from a potentiometer. The motor is then actuated until a specified location is reached. The Due then actuates an arrival bell, actuates a servo to open the door, and then updates an LED matrix with its current floor using a serial protocol known as I2C, which allows us to illuminate 64 LEDs with only 2 wires. Our lift was constructed with mostly repurposed items. The bulk of the material came from a disposed-of IKEA bedside table. The drawer of the table actually inspired the guide rail to help ensure the lift stays in the right position while moving up and down. A speed reduction gearbox was modified to turn a cable drive gear that would pull the lift up and down. This drive gear was rather specific and was able to be salvaged from an old vehicle window regulator as pictured here. You can see it came from the motor housing inside. It was attached securely with some modifications to the reduced speed output of the gearbox. The switches and their accompanying pull-down resistors were mounted onto a breadboard. The Due and the H-bridge were attached to the back of the lift assembly. For our software design, the switches you previously saw are all attached to interrupts, which modify values to tell the lift that it has to service specific floors and which direction to go in. The algorithm is simple in the respect that there are only 3 modes the lift can be in: moving up, moving down, and idle. Because the lift is aware of the direction it is traveling, it can choose to ignore a call from, say, level 2 if it is going in the opposite direction, and then come back to service that floor on its next routine. This works just like commercial lifts, where it limits the amount of time the passenger needs to be in the lift. Upon powering up, the Due takes 3 inputs to manually calibrate the level sensor to ensure proper operation. One early problem was the use of magnetic reed switches. They were meant to assist in detecting the level the lift was on, but they were difficult to calibrate accurately, and also very delicate, as they were in small, rigid glass housings. The potentiometer was originally a backup device, but became the main component for sensing the level. Also, our LED matrix was meant to be animated, showing up and down progress. However, due to the library used to draw images, it would interfere with the lift and cause sporadic operation. Also, our servo was a continuous spin servo, so to achieve specific angles required trial and error and hundreds of calls to the servo controller. Finally, the H-bridge requires complementary pulse width modulated signals to operate the MOSFETs correctly. The first test of our dual timer counters did not have the sync bit turned on, so a 1.5 microsecond overlap caused a short circuit, which caused our fuse to blow. To test the lift, we desk-checked the code under many scenarios, then tested it in simulation before connecting the motor. We found testing small sections of the code at a time proved to be useful, and once we successfully got a component working, we would add one more at a time and ensure proper operation so that we could narrow down any new bugs. In conclusion, we learned a lot from this project, and if we were to improve the functionality of it, our first choice would be to use a stepper motor that has its own position encoding to ensure accurate control of the lift. Additionally, the guide rail does not have the best performance and could be improved with an opposing cable system or rack and pinion drive. Finally, while the breadboard is nice at the onset of a project, it quickly became a nightmare with all the wires, so we would instead prefer to mount them on custom printed circuit boards. We hope you enjoyed this presentation, and thank you for your time.